Hi everyone, and thank you for joining my talk. I'd like to start by thanking the organizers for inviting me to give the talk on image transmission through a flexible multimode fiber by deep learning. Multimode fibers are fibers with a large core that supports multiple guided modes. There's lots of hope that multimode fibers could be used to increase the capacity of information that we can deliver with fibers. But the problem is that even for perfect fibers, when we focus the light at the input facet, we excite multiple modes, and since each mode propagates at a different phase velocity, at the output of the fiber, all the modes will interfere with random relative phases, forming a speckle pattern which scrambles the information we are trying to deliver. The promise and challenge of multimode fibers have raised over the past few years lots of interest in a wide range of disciplines, ranging from basic research on random medium, quantum optics, and nonlinear optics, all the way to technology such as spatial division multiplexing in optical communication and in spectroscopy. Today I'm going to focus on imaging through multimode fibers. The motivation for imaging through fibers is clear, especially for biomedical endoscopic applications, and thus it has a long and fascinating history. Here's a beautiful example from the 1930s by Hendrik Lam, who succeeded to image a filament of a light bulb through a bundle of multimode fibers. So you may ask what is new. We are all now living in the digital era, which revolutionized our approach for imaging, and specifically for imaging through fibers. Since the propagation through fibers is linear, we can completely describe the transmission through a fiber using a matrix called the transmission matrix. In principle, if we can measure how a set of orthogonal modes propagate through the fiber, we can know everything there is to know about the fiber, and we can unscramble the output speckle and reconstruct the delivered images. We can use a spatial light modulator to measure the transmission matrix, and we can also use it to focus the light at the distal end of the fiber and then raster scan the object. Both of these approaches and many others have been widely studied over the past decade, showing remarkable achievements for a wide range of imaging modalities such as phase contrast, dark field, and fluorescence. The problem is that all of these approaches rely on the fact that the transmission matrix of the fiber has to be fixed. It must not change during the acquisition of the image. The problem is that multimode fibers are extremely sensitive to perturbations, and if you slightly touch the fiber, slightly change its conformation, the output speckle can completely change. This is depicted here by three different fiber configurations showing three different fiber speckle patterns at the output of the fiber. This means that the transmission matrix is not fixed, and every time it changes, you need to measure the transmission matrix again. The first thing I want to tell you about today is our approach for trying to utilize the sensitivity of the fiber's transmission matrix to mechanical perturbations and turn it into a positive feature. We wanted to see whether we can apply computer-controlled perturbations to control the transmission matrix of the fiber. We did this using what we call the fiber piano depicted here. What you can see here is an array of computer-controlled piezoelectric actuators. Each one of these gray rectangles is our piezoelectric benders that can go up and down by applying a voltage, a computer-controlled voltage, to each and one of these piezos. The piezos press on a multimode fiber that runs below them, depicted here in this yellow line. So when we change the voltage of the applied to each one of the piezos, we can press it up and down, move it up and down, and this completely changes the speckle at the output of the fiber, because as we said, the speckles are extremely sensitive to the mechanical deformations of the piezos. Now we can look at the output image, the output speckle image, choose one pixel, and run some iterative optimization algorithm to find the voltage we need to apply to each piezo in order to get a desired pattern at the output of the fiber. We used the particle swarm optimization protocol, which we found to be quite efficient for this task, but basically almost any iterative algorithm we tried, like genetic algorithm and stochastic gradient descent, worked. On the left, you can see the speckle pattern before the optimization, And then on the right, you can see the pattern we got after running the optimization to focus all the light to this spot here. The enhancement factor, defined by the ratio of the intensity at the focus spot and the average intensity we obtained, was 25. I want to stress that we achieved this focusing without any spatial light modulator. We got this simply by pressing the fiber along different spots along the fiber. This is all useful since it opens the doors for an all-fiber spatial light modulation simply by harnessing the sensitivity of the fiber to mechanical bends. But still, this approach is sensitive to perturbations, meaning that even if we found the configuration of piezos we need in order to focus the light to this spot, once things move in the fiber, any other perturbation will completely mess up the output pattern, and we'll have to run the optimization again to refocus the light to the right spot. So, as we said, the optimization is sensitive to mechanical perturbations. As I mentioned, the sensitivity to fiber perturbation is common to all imaging approaches, and people have tried to circumvent this sensitivity in all kinds of approaches. Here are two examples. Thomas Sizmar's team has shown that if you know exactly the parameters of the fiber and its transmission matrix, you can predict the effect of bending and compensate for it computationally. This is depicted over here on the left, showing that for image received for a straight fiber is only slightly deteriorated when the fiber is bent. My colleague Sebastian Popovs has shown that once you measure the transmission matrix of the fiber, you can also find a set of modes that are resilient to weak perturbations. This is demonstrated here by showing that the output speckle doesn't change much when we press the fiber with an actuator. Both of these approaches work well for weak perturbations, but what about strong perturbations? What we asked ourselves was whether we can use deep learning to find invariants of the strong fiber perturbations that will help us image through the fiber in a robust manner. In the last few years or so, deep learning has been integrated nicely with imaging through multimode fibers. What people typically do is display images on the input facet of the fiber, using a DIMM-D deformable mirror device, and record the output speckle patterns, and then use a neural network to reconstruct the input images from the speckle patterns. This approach works very well for a single fiber configuration. Several studies have tested how well the network handles perturbations. For example, in this work by Fan et al., the network was first trained to reconstruct images from an MNIST digit dataset. As you can see in the first two rows, the reconstruction works quite well. The top row is the ground truth, and then below it is the reconstruction obtained for a static fiber. But now if something in the fiber moves, in this example, a rod that bends the fiber was moved by just a few centimeters, and then the network failed to reconstruct the image. This is what you see on the third row here. Once the network was trained to learn the input-output relations for multiple positions around the rod, then the network was able to reconstruct back the digits. The problem is that with the moving rod, it is quite difficult to train the network on many different configurations. So this approach worked well only for weak perturbations and for just a few different positions or a few different configurations of the fiber. But with the fiber piano I just presented earlier, we can quite easily train the network over hundreds of strongly perturbed configurations, and therefore hopefully find statistical invariants that will be robust and relevant for many different strongly perturbed fiber configurations. Lei Tian's team, who will also be presenting later in this session, has shown that for scattering samples, deep neural networks can find such invariants. In this work, what we wanted to see is whether this is also true for multimode fibers. So again, we wanted to see whether in multimode fibers, strongly perturbed multimode fibers, a deep neural network can learn some invariants that will help us transmit images through the fiber. Using the fiber piano, we can create, as we said earlier, hundreds of random configurations of the fiber. So, okay, this is depicted by the different conformations of the fiber. And then train the network on them, and in this way make the network more robust to perturbations. So we project them into the fiber images. So we project into the fiber different images of digits. We record the intensity of the speckle patterns at the end and get the input-output relations for multiple different inputs and multiple different fiber configurations. We collect hundreds of thousands of such pairs for different fiber configurations, which we create by different positions of the actuators. We use some of these pairs to train the neural network, and the others to evaluate the fidelity of the reconstruction we get. This is how our setup looks. We have a Heaney laser that shines a DMD that is image onto the input facet of the fiber. Then we have a 1.5 meter long fiber along which we press with 4D piezoelectric actuators, and we image the output speckle patterns on a camera. The actuators induce strong perturbations that are quantified by a low Pearson correlation that we measure for two different speckle patterns obtained for two different fiber configurations, two different configurations of the piezos, but for the same input. And we see that the average Pearson correlation for such between such different configurations is 0.12%. Our network is a convolution neural network in a UNet design with about 2 million learnable parameters. We start with images of 128 by 128 pixels. Then the network contracts the images to smaller yet deeper layers with increasing number of channels, and then it expands again to eventually predict 128 by 128 images. We first start by training the network on a single configuration of the fiber. That is, we define a random set of positions of the actuators by setting a random set of voltages to each piezo, and acquire the image pairs only from this configuration. So we have different inputs, different outputs, but the same fiber configuration. We train the network by sending something like 60,000 digit images, record the output speckle, and feed the network with these pairs to find the network's weights. We also record about 10,000 pairs to later be used for testing. When training is complete, we estimate the network by feeding it with speckle from the test set, which contains only speckles that were not used for its training. We let the network reconstruct the images from the measured speckle patterns and compare its prediction with the actual input which was displayed on the DMD. Here I show a few reconstruction examples for when we train on a single fiber configuration. Qualitatively, you can see that the reconstruction is quite good when we compare it to the ground truth, meaning the actual pattern that we projected onto the DMD. To give a quantitative measure, we calculate the pixel-wise accuracy of the reconstruction, which here appears in orange, and is about 97 or even 98% out of 100%. We also calculate the Descartes index, which is the intersection over union score of binary patterns, which here is about 0.84 out of 1, which is, of course, very high. Next, we wanted to study how the reconstruction fidelity changes with decreased correlations between the training and test sets. In this graph, the blue point corresponds to the reconstruction I showed in the previous slide, where the test configuration is part of the training set. The correlation between the train and test configurations is therefore 1, because although we use different patterns for the training and testing, they all come from the same fiber configuration. Next, we created multiple other fiber configurations by perturbing the fiber with our piezoelectric actuators. So the correlation with the training set got smaller and smaller as we applied stronger and stronger deformations with the fiber. So as we go on this graph from right to left, we apply stronger deformations with the piezos, and therefore the reconstruction fidelity goes down, as indicated by the Descartes index that goes down, and also in these few examples showing the reconstruction of the digit 0, and of course the reconstruction goes lower and lower. All these examples should be compared to the ground truth shown here. Now, what we want to achieve is a good reconstruction for random configurations. Random configurations mean configurations that weren't part of the training set and that are configurations that are strongly perturbed relative to the training set, meaning that have low Pearson correlation with the training set. In terms of this graph, what we want to do is we want to take these low Jaccard index reconstructions for low Pearson correlation between train and test configurations and push it up. We want to find a way to get high Jaccard index reconstructions, high fidelities for low correlations between train and test sets. Our approach for doing this is as follows. We introduced an approach which we call configuration training, where instead of training the model on a lot of data from a few configurations, as was done in previous studies, we train the network on much less data for each configuration, each fiber configuration, but use the fiber piano to induce many hundreds of different configurations. This way, we help the neural network recognize small invariant properties of the fiber configuration rather than the exact transformation of a specific configuration. For that, we acquire data from over 1,000 random fiber configurations whose average Pearson correlation, again the correlation between different fiber configurations for the same input, is about 12%. We use some of the configurations to train the neural network, while the others remain unknown to the network. Once we finish training, we test the model on unfamiliar speckle patterns from known and unknown configurations and looked at the reconstructions it produced, like the one in this figure. The fidelity is not as good as before for a single configuration, but most images are quite similar to the ground truth. Moreover, we can see that there's a strong resemblance by the quality of the reconstructions we get from unknown configurations, that is, configurations that were not seen by the network, and for known configurations that were used by the network. So we can see that our model is robust against mechanical perturbations that are applied by applying random mechanical perturbations with the piezos. This is the first time, to our knowledge, that the bend resilience is being demonstrated to such an extent, and we are quite excited about it. Now we can go back to this graph, and by averaging the Jaccard index we get for the test patterns, we see that the reconstruction produced by our methods, again the configuration training method, resembles the ground truth quite well, as depicted in this example for the 0 digit, while before it didn't really work. In terms of the Jaccard index, we obtain an improvement of a factor of a 3 or more than threefold improvement, which is quite significant. If we compared the Jaccard index we receive for this configuration training, it's comparable to the Jaccard indexes obtained when only weak perturbations are applied to the fiber. I emphasize that this was all done without the model having any knowledge of the fiber configuration in which the speckle was acquired. So again, we're very excited that using configuration training, and the reconstruction fidelities were comparable. The reconstruction fidelities for strong induced perturbations were comparable to the reconstruction fidelities obtained with weak perturbations. Now we can ask ourselves, how can this work? How can the network reconstruct images from unknown fiber configurations? The answer is that different fiber configurations are not completely uncorrelated. Some hidden correlations do survive the perturbations. To depict this, we show on the left correlations between the output speckle for different realizations of the digit 9, but for the same fiber configuration. The Y distribution accounts for the ease of reconstructing images for a single fiber configuration, that is, that the train and test data accounts for the same fiber configuration. On the right, we see the histogram of correlations obtained from speckles generated from two different fiber configurations. In orange, we see the correlations obtained for the same input, and in blue, the correlations obtained for different inputs. In both cases, the distribution is, of course, centered at much lower correlation values relative to the correlations obtained for the single fiber configurations, since this is correlation between two strongly perturbed fiber configurations. But we notice the slight shift between the orange and blue histograms, which means that the fact that the orange histogram coming for the same inputs is slightly to the right means that even though the two fiber configurations are different, are strongly perturbed, and the fiber is strongly perturbed between configurations, still there's a higher, the fact that there's higher correlation for the same input means that some of the information is preserved in the sense that some of the information on the input is still preserved at the output. Based on the fact that some correlations are still present, even for strong perturbations, it is important to ask whether we really need the heavy machinery of deep learning to reconstruct the digits. To answer this question, we try to embed the high-dimensional data spanned by all the output speckle patterns in a two-dimensional space using an unsupervised algorithm called TSNE that applies nonlinear dimensional reduction. For a single fiber configuration, the 2D embedding of 15,000 speckle patterns mostly divides the speckle patterns according to the class of the digit that was displayed on the fiber, namely the 0 and 9. This is the 10 clusters we see here. Such clustering indicates that for a single fiber configuration, again, single fiber configuration meaning that the test and train data were taken for the same conformation of the fiber. So in this case, unsupervised algorithms could have worked, and therefore we believe that a neural network might not have been necessary for this. On the other hand, when we tried this 2D embedding for speckle patterns obtained for 33 random configurations, we see that the embedding contains 32 blobs and an additional center blob that corresponds to data that was not easily separable. The data images, the two images we show here are actually from the same data set. The only difference is the different color coding. On the left, the color code corresponds to different configurations, showing that the unsupervised algorithm can cluster the patterns according to their original configuration. However, on the right, we do the color coding according to the digits, and we see that this unsupervised algorithm cannot discriminate between different digits as depicted here. Okay, the mixing of the different colors show us that this simple unsupervised algorithm could not distinguish digits from different classes. So the unsupervised algorithm failed where the deep neural network succeeded at. And this is an indication on the importance of deep learning for imaging through fibers that are strongly perturbed, especially the more uncorrelated configurations of the fiber we have, the more important it is to have deep learning. So I think I'm running out of time, so this is a good point to stop and summarize. And at the beginning, I've briefly presented you the fiber piano that we constructed that utilizes fiber bends to focus light at the output of the fiber. I then showed a different application of the fiber piano, where we use deep learning to learn the effect of strong perturbations on imaging through the fiber. We saw that the training of a deep neural network on speckles that are generated from hundreds of different and low correlated fiber bends could achieve bend robustness and provide reconstructions even from unknown input patterns and for unknown bends. We therefore believe that training networks on strongly perturbed fibers is a promising route towards achieving robust imaging through multimode fibers. And if you want to read more information, everything I presented here and much more is summarized in these 3 papers. So I think this is a good point to acknowledge my colleagues, and especially Sebastian Popov, our collaborator from the Institute of Langevin, and my fantastic team of students, and especially Shahar Rossisi, who took the lead on the project I presented you today. And of course, I should acknowledge the funding agencies and acknowledge you for listening. And I am looking forward to answering your questions in the live Q&A session. Thank you, everyone.